Are you guys able to see my screen?
Yes, sir.
So today we'll be diving into machine learning. This is our lecture 5, I think. Learning from examples in Bucks. So this is a slide we'll be following. I think this slide belongs to Java sir, and I think most other sections are following this slide. So we'll be following this as well. Well, MGH stands for Mohammed Ghazal Haq. It's a multinational company. Um, it's not software company in particular, but it does have a lot of software that it develops. So it has an IT sector. So I worked as a web developer in the IT sector of MGH. I worked on a software that was basically an accounting software. It was developed by MGH developers, and it ran both in Bangladesh and in Nepal. So I was a web developer in that project. All right. So what we'll be learning today is what is machine learning, particularly inductive learning, because our lecture is learning from examples. That's what inductive learning is. If you divide inductive learning, you get supervised learning and unsupervised learning. Do you guys have any idea what is supervised learning and unsupervised learning? Okay, we'll find out together. So first, uh, we should understand why it's important for us to learn machine learning because, well, we have to understand and improve efficiencies of human learning. We humans are pretty limited, and compared to machines, we are pretty slow and inaccurate. So we can pretty much already have an idea why machine learning is so popular these days because machines are so much faster and are able to predict things so much better than humans by doing massive calculations in a matter of seconds. And today we see machine learning almost everywhere, starting from facial recognitions and Facebook pictures all the way to healthcare, finance, you name it. Machine learning is almost everywhere these days. So there are some major paradigms of machine learning. These are some examples, basically. Um, for example, rote learning is like learning from memorization. Induction is learning from examples. Clustering is a part of unsupervised learning, and so on. There are some examples given in the slide, and in the very bottom one, it says reinforcement learning. That's kind of a feedback-based learning. Okay, let's talk about supervised learning and unsupervised learning. Since we'll be learning about induction learning, we need to clarify our ideas about supervised learning and unsupervised learning. Both of them, you have to. The idea is the machine will learn from examples. But what's the difference between supervised and unsupervised? Well, in supervised learning, you'll be categorizing your data as features and labels. Now, what does that mean? Let's say you're trying to design a model that can identify a human and a dog from images. So you're trying to train a model that can identify a human or a dog. It can differentiate between a picture of a human and a picture of a dog. So what are the features and what are the labels? Um, the the procedure you would have to follow is hold on, someone's trying to join. So the procedure you'll have to follow is, let's say you have 1,000 images of humans and 1,000 images of dogs. So you would have to use those images to train your model. For example, let's say you're feeding your machine 1,000 images of a human being. Now, what are the features? The features can be that a human has two legs, two arms, one head, two eyes, a nose. These are all features of a human being. And similarly, if you're trying to teach the model how to identify a dog, the features can be it has four legs, it has two ears, it has a nose, it barks, and so on. And the label is it's a dog. And for the previous example, the label was it's a human being. So there could be multiple features. Actually, the more the better. So if you're, let's say, you feed your machine 1,000 pictures of a human being and 1,000 pictures of a dog. So now it understands how it learned a little bit and it tried to figure out some features and it understood how to label them. If it found that this picture, the the living thing in this picture has four legs and some other features matching to a dog, it will predict that it's a dog. And if the features match in the training model that it was labeled as a human before in the training model, then in a next unknown image, it will try to match the features and label it there. So that's supervised learning. That you're categorizing your data with features and labels. So what is was I clear on that? Did you guys get the idea how supervised learning works? If you have any questions, feel free to interrupt and ask questions. So in supervised learning, the more data you feed it, the more accurate it becomes. The more features, the more data it has, it, it learns better, and in the future, it predicts better. For the example I just gave, let's say you taught your model how to differentiate between a human and a dog. Then next time when you give a random picture, it will match all the features. If it's a human or a dog, whichever feature matches most, it will predict that this this particular image is of a human, or if it's matched just with a dog, it'll predict that it's a dog. It doesn't necessarily mean it will be 100% accurate. The more it trains, the more it learns, and the more accurate it becomes. It works like that. So for unsupervised learning, the thing is we're not going to label anything for the model to learn. An example can be given. Let's say in a basket, you have two different kinds of fruits. You have bananas and you have oranges. Now, if you give a baby, now how does babies learn? If you give a baby a basket and just tell the baby to differentiate between them, the basket contains two different kinds of fruits, bananas and oranges. Now, the baby doesn't understand what's a banana, it doesn't understand what's an orange, so it doesn't know the labels. However, the fruits are different, the shapes are different, the colors are different. They can be categorized into subcategories. They can be clustered into multiple groups. But the baby itself does not know what's a banana and what's an orange. So that's how unsupervised learning works. You're not labeling the data. You don't have any idea what those things mean. You have a chunk of data that you want your program to make sense of. So you feed the entire data. You don't label anything. And what your program should do is try to find different patterns by itself and categorize the data into clusters. And in the end, all it will say is, I found three types of data or two types of data. This is type 1, this is type 2, that's type 3, and so on. It doesn't know what's a banana, it doesn't know what's an orange. All it knows is it's found different kinds of data, and they were able, uh, it was able to cluster them in separate groups. Is the idea clear about supervised learning and unsupervised learning? Again, if you have any questions, feel free to interrupt. If you guys are clear so far, let's move on. Now, we'll be learning mostly induction learning, which is basically supervised and unsupervised learning. So, two popular, uh, two popular uh, ways of supervised learning is classification and regression. In the slide, there are some examples given how how they work, but there are some major differences between classification and regression. If we go to the next slide, we'll we see a graph like this. Let me explain this. In classification, we are classifying. Um, we're classifying into multiple groups, but in regression, we are trying to predict a certain value. For an example, in regression, let's say if we were using our model to predict tomorrow's weather, if we used regression, it would give us an exact value. Let's say we fed it data for the last 30 days of weather, and we are trying to predict that what would be tomorrow's temperature. So based on the 30 days of given data about the weather, it will try to predict what will be tomorrow's temperature. So after training the model, and uh, it will predict something like 84 degrees Fahrenheit. If we use regression, let's say in our previous data, it was around 84. Let's say yesterday it was 83. Before that, it was 85. Things like that. So it predicts a value that tomorrow it predicts that it'll be 84 degrees. But in classification, you would have to classify your data into multiple groups. So in classification, you won't be asking what will be the temperature tomorrow. You will be asking is, will it be cold or will it be hot tomorrow? So your data has to be organized, and it also has to fall under different classes. So in your training set, it should say like past 30 days, like yesterday it was cold, and you have to set a range that if the temperature is let's say below 80 degrees Fahrenheit, you say it's cold, and if it's greater than 80 degrees, you say it's hot. For an example. So let's say yesterday it was hot, before that it was cold, and before that it was cold again, things like that. And if you're trying to predict a model, use the model to predict tomorrow's weather, it will rather have options of classes instead of an actual value. That's the basic difference between regression and classification. In classification, you actually have to divide the possibility into different classes, and regression, it will be a value. The machine will predict a value. Um, I hope you're clear on that. If you do have questions, again, you can ask anytime you want. So there's some more detailed examples of classification. Each record contains a set of attributes. One attribute is the class. Previously on the same data. So yeah, we pretty much talked about all this. Right. So So there's an example given. I hope after seeing this, it'll be even more clear to you. Let's say this is our training set. This is like our attribute 1, attribute 2, attribute 3. So these are our attributes or our features, and this is our label, class, yes or no. So this is an example of a classification. So we have two classes, yes or no. After feeding this data to train our model, you see that the arrow says induction, learning model. We have to choose a learning algorithm, and then uh, after this process is complete, we will have our model, our learned model. This model learned from this data set and now is trying to predict something that we don't know. This is the test set. So these are the values we don't know. After teaching the model, we will apply some new data to it that it never seen before and try to predict the outcomes of those data. This is how a simple classification learning would work. Right, so there are some examples given in the slide. Classification is used for predicting tumor cells, classifying credit card transactions as legitimate or fraud, classifying secondary instructions, protein alpha. So, and also categorizing news stories is fine as well. Okay, so there are some examples of where classification learning is used. Okay, um, in this slide, it says that let's say you have a few data in section A. Let's say you have two features, x-axis and y-axis, and this is one of your data. This is one of your data. So the four dots are your data. So which kind of algorithm should we choose to make the most sense? There can be a lot of there are different there are a lot of algorithms, machine learning algorithms, and it's completely up to you to which one to choose. For example, in B, it says that it used a function that was precise, piecewise. It used a piecewise function. In C, it says it used a smooth function. In D, it says that it used something else. It chose simplicity and rather even neglected one of the data. So what this slide is trying to say is there are multiple ways to solve a machine learning problem, and different people might choose different algorithms, and they might have different outcomes based on that. So what is bias? It says a preference for one over the other reveals the bias. Some people might go for an approach like this. Some people might go for an approach like this. So a preference over one over the other is known as bias. So this concept that some people going for different approaches and some people going for other approaches, this concept is known as biased. We'll be learning more about this in an upcoming slide. So let's keep on going. All right. So in this particular slide, it says basically that if all the features are P, and we can represent them like this, and we have to train a model, and if our model space is M, there can be possibly infinite model spaces. Again, when we do examples, this will be much more clear to us. So for now, I'm just moving on. So what are model spaces? There can be multiple model spaces. For example, it's basically which algorithm you are using for um, trying to solve a problem, to trying to teach your machine, to trying to train your machine. In the slide, there's a few examples like decision trees, nearest neighbor classifiers, Bayesian networks, neural nets, support vector machines, and so on. These are different algorithms, machine learning algorithms, and we'll be looking at the decision trees in this particular slide. So, what is the decision tree? It looks something like this. Um, we have to, based on the given data, we would have to come up with a tree like this so that our machine can predict a value, predict a never seen before value. There's a better example on the next slide. Let's try to understand what's going on here. Are you guys following along, or if you're confused about anything? Or if I'm going too fast? I'll be giving you the slide once we're done with this lecture. I think I'll be posting the in your classroom. Okay, back to the slide. Let's try to understand what's going on here. So based on this data, it says that decision tree like this was made. For example, if let's try to look at the data and try to make sense of the decision tree. Saying if the refund is yes, okay. I think this training data is basically of people who cheated or not. So there are three attributes or features: refund, marital status, and taxable income. So based on these attributes, our machine will try to predict if a person cheated or not, yes or no. So it's saying based on the training data, if the refund is yes, if the person did take a refund, if the refund is yes, the person did not cheat. If we look at the training data, in every case, if the refund is yes, we see that the cheat is no. Again, in fourth row, the refund is yes, and the cheat is no. Again, in the seventh row, it's the same. So, in based on this particular training data set, our decision tree model says that if the refund is yes, then cheat will always be no. But what if the refund is no? Then we have to depend on the other attributes or the features. Then it says that if marital status is married, then the person did not cheat. So when the refund is no and marital status is married, our model says that the chances of the person not cheating is very high. So if refund is no and marital status is married, we see that in our training data set, it says no. So what a decision tree is it tries to make sense of a training data set by creating a tree like this. So if the refund is no and the marital status is divorced, then it will look at the taxable income. If the taxable income is greater than 80K, then it's predicting that the person did cheat, and if it's less than 80K, the person did not cheat. So this is based on the training data set. Now after creating the decision tree, we have to predict a value that was never seen before. For example, in this particular. says this is a new value, and we don't know if the person cheated or not. So our model has to try and figure out the outcome. So let's see what happens. It says that refund is no. So after coming here, it will move to this side on the right side because refund is no. Then it needs to check if the marital status is married or single or divorced. So it checks the refund and no, and then it checks the marital status. It says married, so our machine predicts that the person did not cheat. The answer is no. Is this clear to you guys? How a decision tree works? I'm not getting responses, so I'm a bit confused if I'm going too fast or you guys are having trouble catching up, or is it fine? Any questions so far? Okay. All right. Now let's move on to information theory. What does the information theory say? The information theory says that the information conveyed by a message depends on its probability. With n equally probable possible messages, the probability p should be 1 by n for each of them. So if there are n messages, the probability of each message would be 1 by n, right? Um, on the next point, it says that information conveyed by a message is log base 2 n, and this is equal to log base 2 p. And this is an example given. Okay, let me give you an example how this works. What this basically is saying that to represent any kind of information, how many bits do we need? In this example, it says if there were 16 messages, we would need 4 bits. Let's start with a smaller example, how this calculation actually works. We are all familiar with binary, right? Bits, zeros and ones. So if we're trying to represent, let's say, 3 messages instead of 4, how many bits would we require? Well, actually, not 3 messages. Let's say we are trying to represent 8 messages, and my question is, how many bits do we need? If this is too confusing for you, let's start with 2 messages. If we want to represent 2 messages, we would either need 0 or 1. 0 for the first message, 1 for the second message. So this would mean 1 bit, because that's 1 bit, 0 or 1. So imagine you have like empty cells. So to represent 2 different kinds of value, you would actually need only 1 bit. And the value of that bit can be 0 or 1. 0 can represent the first value, 1 can represent the second value. For 4, if we want to represent 4 messages, how many bits do we need? We can go with 0. Yeah, okay, so we can go with 0 and 1. That would be 1 bit. And how can we represent the other 2? We would have to require another bit. we would have to require another cell, and then we can represent them by 1 0 and 1 1. So if we're trying to represent four four messages, it would be 0 0, 0 1, 1 0, and 1 1. So these are our four messages. Similarly, for 8, we would need 3 bits, right? 0 0 0, 0 0 1, 0 1 0. You get the idea, right? In binary, if we're trying to represent from 0 to 7, we need 3 binary digits and 0 1 1. So this is 4. And if we use them again with 1 at the starting index, we get all 8 binary digits. So this is what it's saying, that if we wanted to represent 16 messages, we would need 4 bits. 0 0 0 0, 0 0 0 1, and so on, and the final bit would be 4 ones. So if that is clear, then we can always go for log base 2 times the messages. Then we'll always have a right answer, because we are trying to figure out how many bits do we need. And each bit can contain 0 or 1. That's why it's log base 2. So, and in this case, so what does this mean? Log base 2n should equal to minus log base 2p. P is the probability, which is 1 by n. Okay. So in log, we know that if we have a negative sign at the very beginning, it's basically to the power minus 1. So 1 by n to the power minus 1 is actually n. So this is how we can say that log base 2n equals to minus log base 2p. Okay, is the idea clear about information theory? Next, we have something called entropy. There's a equation given to calculate entropy, but let's find out what entropy really is first, and why do we need it. So remember, in a previous example, we learned about decision trees, right? In this particular example, based on this training data, we created this decision tree. But now the question is, how did we create it? Why did we put refund at the very top? Why couldn't we put marital status or tax income and then have branches from those? What would be the problem there? In the previous slide, we showed that there are multiple ways to solve a problem. Some will go this way, some will go that way. Now, for decision trees, there's a concept called entropy. What calculating the entropy does is it gives us the impurity of a training data. What that means is, when we understand that which attribute it would be more beneficial to us for choosing as the root node and so on, and practically the sequence. If we calculate the entropy, we would find out which node would be more beneficial to us if we choose them first. In this particular case, after calculating the entropy, it told us that choosing refund would give us the optimum answer, and after that, we should choose a marital status, and after that, taxation. So, how do we calculate the entropy, and what does entropy really mean? The calculation of entropy can be a bit lengthy. I'm not sure if I should start now or in class. Let's keep going as far as we can. Okay, so this is the basic calculation of they're calculating the entropy. If we try to look at this graph, the entropy should be between 0 to 1. It can be any value from 0 to 1, and this is the equation for calculating entropy. So what does this mean? It means that P of positive, that means in our final outcome, let's say there are two possible answers, yes and no. So the probability of yes would be P positive, and we have to multiply that with log 2 times P positive, which is again the probability of yes. If our decision tree has two final outcomes, yes and no, it would be the probability of yes times log probability of yes. And notice there's the minus symbol at the very beginning, and there's also minus symbol at the middle. And we have to do the same thing for probability of no, which is p minus, and log 2 probability of no. Now, what does these mean? If we look at this example, impure and pure sets, we see that in our training data set, if let's say there are 6 rows and 3 of them are yes and 3 of them are no. So what would be the probability of yes in that case? There are 3 yeses and 3 nos. There are total 3 plus 3, 6 rows of data. So the probability of yes would be 3 by 6, right? 3 yeses out of 6. So 3 by 6 would be right p plus, and log base 2, 3 divided by 6. We basically did this part, and minus, and the probability of no is also 3 by 6 because there are 3 no's out of 6 possible no's. So it's again 3 by 6 and log 2 3 by 6. So after using the formula to calculate entropy, we will get something like 1. And in a pure set, let's say if all the values are yes or all the values are no. In this particular example, it says that all the values are yes. In that case, if there are four rows of data and all of them are yes, then it says that if we try to calculate the entropy, it would give us 4 divided by 4 log 2, 4 divided by 4. And this is 0 and this is 0. So 0 minus 0 would actually give us 0. So why are we calling the first example impure and the second example pure? Well, in our training data set, if we have mixtures of yes and no, that would be an impure data set. Pure data set is when all of the training data set is yes or no. That means there are no other possible outcomes. It's either all yes or all no. In this case, if it was 0 yes and 4 no's, it would have been a pure data set as well. Let's look at a few more examples. We'll hopefully we'll understand better. In this example, it's saying that this is an impure data set and this is a pure data set. That we were able to completely differentiate between unemployed and employed. But in this case, if we try to categorize between 50K and less or equal 50K, there might be some values like there's a plus symbol on the left side and there are some circles on the right side. So this is trying to uh, visually represent how a pure set and unpure set can look like. So it's saying that entropy really means is we're trying to calculate the impurity in our group of examples. Some more visual representation. This can be a very impure set. This is a less impure set, and this is minimum impurity because there's nothing else but one group of data. So it's very similar to the all yeses or all nos, and in this case there can be multiple yeses, multiple nos, and so on. Okay, so it's saying that when we have a pure minimum impurity, that means a completely pure set, that is not a good training set for learning. Can anybody tell me why? What does an impure set mean? It means that all the data are either yes or no. So choosing a data set like that, it's saying that it's not a good option. Can anybody guess why? Does that? Well, if you're trying to train your model and you're using a completely pure data set, the problem there would be that it will only be able to identify that one solution. If we go back to our uh, identifying a human and a dog example, if you only feed it data of human, it will never understand how to differentiate between a human and a dog. Or if you give it only data of a dog, while it would be very pure and it will learn how to identify a dog, but if you give a picture of a human, it will just go blank and say that that's the dog too. It'll say everything is a dog. It'll say you are a dog. It'll say your friend is a dog. So that's not a very good training set. Rather, if you have like maximum impurity, your model will learn better. If you give examples of humans and dogs and you have mixture of them, then your model will learn better in predicting something that it didn't see before. I hope the idea is clear. Okay, moving on. So it's basically the same equation again to calculate the entropy. Let's actually see an example. Okay, so there's something also called information gain. Um, we'll be calculating entropy and information gain in an upcoming slide. So I think it'll be easier for you once we see an example. So there are some more equations given. Looking at these might might be a bit confusing at the beginning, but like I said, once we're done with a few examples, then we can. I hope it'll be clear to you. Okay, so here it is. Here's our example. Let's see what time it is. Should start. Are you guys okay? This might be a bit lengthy. Are you guys able to catch up so far? We'll be calculating the entropy and the information gain and how actually decision trees are made. The process might be a little lengthy. I don't think we can finish it if we start today, but if you guys want, I think we can go as far as we can for today. Are you guys okay with it? Should I keep going? Any questions so far? So this is our data set. training data set, and we will have to try and figure out a decision tree from this. So the first thing we have to do is calculate the entropy of our decision or our final output. In this particular training data set, what are the features? The features are outlook, temperature, humidity, and wind. And this is my label. This is what we have to predict for unknown data in the future. So the first thing we have to do is calculate the entropy of our output, or in this case, the decision. So if we use the equation of entropy, we see something like this, that the entropy of decision, which is our output data, will be minus of probability of yes times log 2 probability of yes minus probability of no times log 2 probability of no. So if we look at the training data set one more time, we will see that in total there are 9 yeses and 5 nos. The no's are in row 1, row 2, and row 6, row 8, and row 14. So since there are 14, we have 5 no's. So 14 minus 5 is 9. So we have 9 yeses. So if we try to calculate the entropy, we'll get something like this. The probability of yes should be 9 divided by 14. Since there are 14 data, 14 rows of data, and 9 of them are yes, so the probability should be 9 divided by 14 times log 2, 9 divided by 14, minus, since there are 5 no's, should be 5 divided by 14, log 2, 5 divided by 14. So it gives us something like 0.94. This is the entropy of decision. Now we have to figure out which should be our root node in our decision tree. Which of these features or attributes should we choose first in order to get the best outcome? To do that, we have to calculate sorry, we have to calculate the entropy for all of those attributes. For example, okay, in this example, it shows us that if we try to calculate for wind, entropy for wind, what will it look like? So how many values does wind have? It has weak, it has strong, and that's pretty much it. It has either strong or weak. So we have to calculate wind for strong and wind for weak. The entropy of wind equal to strong and wind equal to wind equal to weak. And after that, we would have to use this value and subtract from it the entropy of wind equal to weak and wind equal to strong. We'll go step by step. So first, let's try to calculate the value of if the entropy of decision while wind is equal to weak. So from our training data set, if we only pick the values where wind is equal to weak, we get this table. So and now let's try to calculate the entropy. So again, the equation is same. The probability of yes times log probability of yes minus, there's a negative sign at the very beginning. The probability of no times log base 2 probability of no. It's the same equation. In the previous equation, it says yes first and no second. It doesn't really matter. They both have negative signs at the beginning. So you can write no first, yes later. It doesn't matter. In this example, in this slide, it says that trying to calculate the entropy of decision while wind is equal to weak. So how can we do that? After separating the data where wind is equal to weak, we get this table. So based on this table, we have to calculate the entropy. So again, it's saying that first let's calculate the probability of no. So while wind is equal to weak, how many no's and yeses do we have? We have one, two no's out of one, two, three, four, five, six, seven, eight. So there are eight rows where wind is equal to weak, and among those eight rows, there are two no's and six yeses. So if we try to calculate the entropy, we'll get something like this. There are two no's out of eight, so the probability of no would be 2 by 8, and log base 2 by 8, minus the probability of yes would be 6 by 8, since there are 6 yeses out of 8, times log 2, 6, 8, 6 divided by 8. So we get the entropy something like this. If you put this in your calculator, you'll get something like this, 0.81. So now we have to do it for wind equal to strong, because remember there were two possible uh, values for wind, weak and strong. So if we do it for strong now, again, we're trying to separate the data. For wind equal to strong, we get these values. So how many rows do we have? 1, 2, 3, 4, 5, 6. So we have 6 rows where wind is equal to strong. So let's calculate the entropy of decision while wind is equal to strong. So again, P of no, that means probability of no. How many no's are there? 1, 2, and 3. So 3 no's and 3 yeses out of total 6 rows. So it should be 3 divided by 6 times log 2, 3 divided by 6 minus, for yes is also 3 divided by 6 since there are 3 yeses, 2 divided by 6 times log 2. So if you put this in your calculator, you'll get something like 1. Now, does this look familiar to you? Is this a impure set or a pure set? This is an impure set, right? If there were all yeses or all nos, that would have been a pure set. This is a completely impure set. This is so impure that it's very hard for us to even differentiate between anything because there are three yeses and three nos. So based on wind is equal to strong, we can't really say anything. Just if we try to differentiate between the only condition given is wind is equal to strong, we can't say anything because there are three no's and three yeses. So it's very difficult for us to make a decision here. So that's why this is a very impure set, and as a result, we get 1 maximum impure. Now we can turn back. Okay, now we will try to figure out the gain, the information gain. So entropy stands for impurity, and what information gain stands for is how much information can we gain if we choose wind as our first root node in our tree. So the higher the gain, the better it is for us. Now, how can we calculate the information gain? Remember, at the very beginning, we calculated the entropy of decision. I'll quickly go back here. Entropy of decision, which was 0.94. How did we come to this value? We used the very first table, the given table to us, and calculated the yes and the no's. We used the probabilities of yes, the same equation for entropy. We used that, and we got this value, 0.94. So we have to calculate the gain, first we have to use that value minus, and then we calculated the entropy of decision while wind is equal to weak in the previous slide, right here is 0.811. And In this slide, we calculated the entropy of decision while wind is equal to strong, which is basically 1. So the equation tells us that we have to use the entropy of decision minus probability of decision while wind is equal to weak times entropy of decision while wind is equal to weak. We calculated the entropy of decision while wind is equal to weak in the previous slide, right here. So now, how can we calculate the probability of decision while wind is equal to weak? Any ideas?
So we just have to pick up the number of what do I say parameters of wind being weak from the total number
Exactly.
of
Yeah,
data
exactly.
sets.
Exactly. So in this table, how many rows do we have where wind is equal to weak? We have 8.
Say
So in total, we had 14 rows. So the probability of decision while wind is equal to weak should be 8 divided by 14. That's how we got this value. So we have to multiply this value with the entropy of decision while wind is equal, which was right here. We calculated it while wind was equal to weak, the entropy of decision. Similarly, we have to do it the same thing for wind is equal to strong. So first we have to calculate the probability of decision while wind is equal to strong. How can we do that? We have 6 rows here, 1, 2, 3, 4, 5, 6. And in total we had 14 rows. So the probability would be 6 divided by 14. And the entropy of decision while wind is equal to strong, we calculated that as 1. So it should be 6 divided by 14 times 1. So the information gain of the decision, comma wind, that means if we're trying to figure out decision and taking wind as a root node, the information gain we get is after calculating this equation is 0.048. Now, what does that tell us? That tells us that we need to do the same thing for the other attributes and calculate their information gain. And after that, we'll get something like this. I really wanted to show you how these values come. I wanted to show you for Outlook at least, but I don't think I'll be having too much time for this class. What I want you to do is I want you to try to calculate the Outlook. Go through I'll be giving you the slide right after this lecture. So go through these slides and try to calculate the value. In the slide, they calculated the value for wind. There are two possible values for wind. Wind can be weak or strong. So in Outlook, there are 3 possibilities. It can be sunny, it can be overcast, and it can be rain. So what you would have to do is first calculate the entropy for decision while Outlook is equal to sunny. And then while Outlook is equal to overcast and while Outlook is equal to rain. So you have to calculate those 3 entropies. After calculating those, you have to finally calculate the gain or the information gain. And if you try to compare, here it is, the gain. So it should be gain, decision, comma, outlook. And this would be same, the entropy of decision, which we calculated at the very beginning. So then it would be minus probability of decision while outlook is sunny times entropy of decision while outlook is sunny minus probability of decision while outlook is rain times entropy of decision while outlook is rain, and lastly minus probability of decision while outlook is overcast and probability, times entropy of decision while outlook is overcast. So after using the same methods and same equations, you'll get this value. But like I said, we'll do it together, hopefully in the next class. I don't think I will have enough time to do it today. Um, I'll quickly share what this actually means. Why are we calculating the information? So after calculating the information gain for all the attributes in our given table, wind, humidity, temperature, outlook, we have to compare them. So the more the better. The largest value means that if we choose that particular attribute as our root node, we would get the maximum information. So that will help us branch out the tree to be more efficient. So in this particular case, after calculating the information gain of outlook, temperature, humidity, and wind is here, 0.048, we see that maximum is outlook. So it's saying that the most efficient would be to start off with outlook. And after that, we have to do more steps to finally come up with a tree like this. So we'll be doing all of that together in the next class. And we'll also see some problems if and how to improve some situations. And finally, we'll see something like measuring water quality and cross validation. So we'll be covering all that in the next class. Um, so far, I I hope you understood how we can calculate the entropy and how we can calculate the information gain based on a given data set. And what I want you to do is after I provide you with the slide, I want you to try and calculate these values at home for just for practice because in your exams these types of questions might occur. So it's best if you get some practice right away. From the in the next class, in the very beginning, we'll calculate this together, and we'll draw the entire decision tree. We'll figure out how every step works. So, any questions?
Sir, do you have to infer directly from the entropy values? For instance, in this case, we have only shown like what happens if the entropy value is 0 or 1, like if it's a pure set or impure set. And what if it comes in between the values 0 and 1? So
Yeah, we already seen an example like this.
it's like if the value comes to 0.23 or
Yeah, it can.
0.78.
Of course, it can. If you look at here, for example, if wind is equal to weak, it says that it's 0.81, and for wind is equal to strong, that it's at 1. So this is a completely impure set, but this is something in between, right? 0.81. So the value can differ from 0 to 8 depending on your data set. Sorry, the value can vary from 0 to 1. So it will be a fractional value between 0 to 1, or it can be a completely pure or impure data set. Was I able to answer your question? Or are you still confused about anything?
Sir, I was like thinking, what do you have to infer? Like, if we get 0.11, like, should
Yeah.
it be more on the stronger side or the weaker side? Do you have to infer something like this from the value that we get?
Okay. So what does entropy stand for? It stands for impurity.
Yes.
So the larger the value, we can infer that our data set contains more impurity. Now, if you're trying to train a model, we have to try to pick an impure data set, because if we go for something completely pure, our model won't learn. Will only learn one thing, and will never learn the other thing. So our aim should be um, the lower the entropy, the higher the gain. So our aim should be to figure out which attribute gives us the maximum gain.
And sir, from the gain we can choose the
You can,
root node.
yeah. Actually, we can choose all the nodes. After choosing the root node, we have to choose the second node and the third node. We have to complete the entire tree. So after choosing the root node, we would have to calculate all the entropies again, and then and the information gains as well, and then we would have to figure out which gain would be higher than.
Okay.
So that's how we would draw a decision tree. To be, like I said, you can draw a decision tree multiple ways, but this particular algorithm tells us how to draw the most efficient decision tree based on the data set. And there's also a problem with this approach. We can talk about that and how to do that. Hopefully, we'll be covering all of that in the next class. All right. Any other questions? Okay, if you do still have confusions, I recorded the whole thing. I would suggest to go through the recording again, and I'll be providing you with a slide very soon. And I think if Shitapa told me to upload these lectures in bucks, these live sessions as supplementary material, so I'll be doing that as well. And also, I think there will be a lecture on decision trees from Berkeley University. I think most of your lectures are from University of California, Berkeley, right? I, I, I saw a few previous lectures. So anyway, I'll be uploading all of this in Bucks and also in your classroom, so you can watch this later on. And I think other sections will be doing the same. So in Bucks, you'll see multiple section live sessions covering the same topics. So if you're confused over certain topic that I taught and you're not completely clear about those things, you can also watch the lectures of other sections as well to clarify. You can always reach out to me. I'll definitely try my best to clarify everything. But still, if you're not happy with that, you can look for the other live sessions in other sections as well. So, any last questions, or I think I'll end the live session here, and I'll be giving you the recording very soon, also with the slide. All right. If you do come across any questions while watching this again or going through the slides, make sure to reach out to me. You can let me know in the classroom, or you can email me directly, whichever is convenient for you. So I think I'll end it here. I think we have our next class the day after tomorrow at the same time. So try not to miss it. Try if you're free, if you have stable internet connection, I would suggest you to join the class and tell your friends. Okay, I think I'll end it here. Thank you guys for coming, and take care of yourself.